Hello, hi everyone, welcome back to the channel. So today in this video lecture we'll be solving this problem, minimized maximum of products distributed to any store, which is a yet another problem in this binary search playlist. So let's read the problem statement. So you're given an integer n which represents there are n specialty retail stores. So we have n stores and there are m products type. We have m types of products which has varying amounts, and those products are given as a zero indexed integer array named quantities, where each element in the quantities array represents the number of products of ith product type. Okay, now what do we have to do in this problem? We need to distribute all products to the retail stores following these rules. Okay, so we have n stores and we want to distribute these products to those stores. A store can only be given at most one product type, so we can't give a particular store more than one product type, but can be given any amount of it, probably zero as well. Okay, after distribution each store will have been given some number of products, possibly zero, so we may end up not giving any product to some shop. Let x represents the maximum number of products given to any store, so x represents the maximum product count which we can give to any store. Okay, if it distributes the products somehow. Now what do we want to do in this problem is to minimize that x, which is the maximum number of products given to any store. We want to minimize that. We want to minimize this x. We want this as small as possible. Okay, now that's the problem statement. We have to return an integer representing the x, which is the minimum of the maximum number of products that can be given to any store. Okay, again binary search pattern, minimize x such that we can distribute these products to these given n stores in such a way that x is basically the maximum of the products given to these stores. Okay, fine. So let's better understand the problem statement using an example. So now this is an example. We have 6 stores and we have 2 product types. The first product type has a quantity 11 units, while the second product type has quantity 6 units. I want to distribute these products to these 6 stores. So let's name these stores A, B, C, D, E, F. So we have 6 stores. Let's try to distribute these products to these stores. One of the methods to do so is let's take the very first product type and let's distribute it. So let's say we give 2 units to the very first store, we give 2 units to the second store, we give 2 units to the third store, and then we give, let's say, 5 units to the fourth store. We have distributed the product of type 1. Now let's move to the product of type 2. Let's distribute this. Let's say we give 3 units of this product to shop number E. Let's give 3 products to this product to shop F. Now maximum quantity given to any store, any retail store out of all these products delivered is 5. This is one of the possible distributions. So this is basically x. That's what this x represents. We distribute these given quantities of products to these stores according to the rules given, which says that we can't give 2 product types to a single store. A single store will receive a product of only one type, and the second rule says that we can also give, let's say, 0 products to any store. So let's take another distribution. Let's say we give no product to the shop number A. Let's say I give 4 products to shop number B. Okay, let's say I give 6 products to shop number C, and these products are of type 1. Okay, now let I give one product of type 1 to shop number D. Now let's distribute product number 2. Let's give 4 products of type second to shop number E. Let's give 2 products of type 2 to shop number F, and the maximum in this case would be 6. And now this is basically X. What I want to do is to minimize this X. I want to minimize this X. How can I do that? Let's see one more type of distribution. So the very first product has a quantity of 11. Let's distribute 3 units of this product to A, 3 units of this product to B, 3 units of this product to C, and 2 units of this product to D. We distribute product number 1. Let's take another product which has a quantity of 6. Distribute 3 units of this product to E. Distribute 3 units of this product to F. Now the maximum in this case is 3. Okay. Can I get 2? Let's see that. If I want to get 2 as the minimum, then any distribution, any number of product or quantity of product given to any retail store must not exceed this 2. So let's say I distribute 2 products to shop A from product of type 1. Then I give 2 products of type 1 to shop B. Similarly, 2 products to shop C, 2 products to shop D. And in this fashion, I distributed 8 products, and I distribute 2 more products to shop E, and I distribute 1 product to shop F. And I have distributed the products of type 1, but all of the shops has received the products. In this case, if I go with this type of distribution where I don't have to exceed 2, I'm assuming that 2 would be the minimum product given to any shop. But if I do in this fashion, then I will end up not distributing the product number 2 to any store. So we still have 6 product units to be distributed, but all of the shops have received at least 1 product. That means 2 is not achievable. Since 2 is not achievable, obviously we won't be able to achieve 1, because in all of these cases from 2 onwards and less than 2, basically we will always have some products left, but we want to distribute all of the products to the shops. That means 3 is the answer for this test case. 3 is the minimum X achievable, or the minimum of the maximum product delivered achievable. That's what we can achieve. We can't go less than 3. And the answer for this test case is 3. Okay, fine. So you got what we are trying to do here. We basically distribute the product to the shops such that each shop receives a product of only one type, and the maximum product received out of all the retail stores must be minimized. That's what I'm trying to do here. Okay, so let's build the intuition. Let's try to solve this problem in the next slide. Okay, so let's take this same example. We have 6 shops. Let's call them A, B, C, D, E, and F. And I have these 2 types of products. The first product has quantity 11 units. The second product has quantity 6 units. Okay, now what is the optimal way to distribute the product such that the X is minimized? So this is X. This is the column for X. Okay, so we can see that X is the monotonic. X is monotonic here. Why? Because let's say, because I want to find X. X is the answer, and we have to binary search over this X. We want to binary search this X, and because this is the answer, and this also has the monotonicity. Why? Let's see that. Now let's say X is the answer for this test case. That means X represents the minimum of the maximum products delivered to any retail store. If x is the answer, like in this case x was 3, then I cannot go less than x. That means I can't achieve answer that is x minus 1. I cannot find x minus 1 as the minimum quantity of product delivered such that it is maximum among all of the other products delivered. Similarly, I can't achieve x minus 2 as well, and so on. While, and what would be the left extreme? It would be 1, because in the worst case we may have, let's say, at least one shop, and we may have, let's say, in the quantity array we may have at least one product which has a quantity of 1, and in this kind of case we just have to deliver this only product to this only shop, so the answer would be 1. So that is the extreme case, that is 1. Okay, now let's think of another extreme. If this x is the answer, here you see, if I can distribute the products in such a way that I can get 3 as my answer, 3 is the minimum number which can be achieved in this case, or minimum amount of product distributed to any store among all other products delivered, then I can always achieve 4. Okay, got it? I can achieve 4. Let's say how. Let's say let's distribute let's start distributing product number first. I distribute 4 units of it to shop A, 4 units of this product to shop B. And can I distribute 4 units to shop C? No, I have only 3 units left, so let's distribute it. Now let's move to product number 2. Distribute 2 units to D, distribute 2 units to E, distribute 2 units to F. So what is the maximum amount delivered? It is 4. That means 4 is achievable. 3 is the minimum, 4 is achievable. That means x plus 1 is achievable. Similarly, x plus 2, that is 5, is also achievable. X plus 3, that is 6, is also achievable. So this is valid. X plus 1 is achievable, x plus 2 is achievable, and so on till the point, let's say the extreme one. Let's say we can have a product of maximum quantity 10 raised to the power 5, and we can deliver entire quantity to a single shop. In case we have only one shop, in that case the answer would be 10 raised to the power 5. Okay, this is the right extreme, and this is my answer. That's what I want. And this is good side, let's call it good. This is bad side, let's call it bad. Why I'm calling it good and bad? Because these answers are achievable, these answers are not achievable for this test case. Okay, like for every test case we have a certain x for which we can't achieve the answers less than x, we can achieve the answers greater than x. This is the search space from 1 to 10 raised to the power 5. And now I want to find this x. That's the target. How can I do that? Simple binary search. Initialize 2 pointers, low to 1. This is my search space. High to 10 raised to the power 5. Okay, find the middle element. Let's call it mid. What does this represent? This represents that, okay, I'm assuming that the mid is the answer, or mid represents the minimized number of products which can be delivered, or mid represents the minimum of the maximum products delivered to all the stores. That's my answer. Then how would I check if this mid lies on the good side or it lies on the bad side? That means if it is possible to get mid as the answer, to deliver mid products such that they're the minimum of maximum number of products delivered to any store. How would I check that? Now that is checked, let's say, using some predicate or boolean function. That's, let's call it is valid. Let's say we have a function is valid. So this is valid function basically checks if this particular mid that we have guessed lies on the bad side or it lies on the good side. If it lies on the good side, then that is the case number 1. In that case, this can be my answer. So let's say it lies here, mid lies right here, then it can be my answer. So I store this mid into an answer variable, and the search space is reduced to low to mid minus 1. Why? Because I may find my first element or even a lesser number which satisfies the given conditions or which is also valid. That is this one. So that's why maybe our answer lies in this range, while this can be the potential answer. So the search space is reduced to this one. Otherwise, the search space is reduced to mid plus 1, too high. In case if this mid lies on this bad side, that means the answer lies on this side only. Okay. Now, how would I check? So in this fashion, I will keep reducing the search space until I reach this x, where I return this x as the answer. Now the next challenge is how would I find this is valid function? What is the definition of is valid function? Let's see that. Okay, so let's say I guessed mid as the minimum of maximum number of products delivered to any stores while satisfying the given conditions. Okay, now I want to verify if this is valid or not. How would I do that? Since we can end up delivering at least 0 products to any store, that means we can deliver 0 products to any store, no issue in that. I can simply start assigning mid products or start delivering mid products to each store. So let's pick the very first product, that is, it has a quantity of 11. And now let's traverse the stores. Let's go to the store number 1 and I deliver mid products to it. Let's say mid is 3. Let's say mid is 3. So I deliver 3 products to shop number A. I have 8 more products of type 1 remaining. Then I deliver 3 products to shop number B. I deliver 3 products to shop number C. And now I have 2 more products to deliver for type 1. So I deliver 2 products to shop number D. Jump to product number 2. Deliver 3 products to shop number E. Deliver 3 products to shop number F. I have delivered both of my products to these shops. And here in this case, the maximum of the products delivered is 3. That means it is possible to achieve this 3. So I would look for a better answer. Let's say if we guess mid as 4. Is it possible to achieve 4? Let's check that. Let's start assigning the products from the very first store. Assign 4 products of type 1. Assign 4 products of type 1 to store B. Now assign 3 products of type 1 to store C, because 3 are the remaining products of type 1 that we have. Now I have delivered product of type 1. Let's jump to product of type 2. Deliver 4 units of this to shop number D. Okay, we have 2 more units. Deliver 1 unit to E, deliver 1 unit to F. This is the division. I can achieve 4 as well. Okay, or let's say deliver 2 products of type 2 to shop number E, and deliver 0 products to shop number F. This is also valid. This is also valid. Okay, so let's say if I want to deliver 10 products, let's call 10. If x is 10, can I achieve 10? Let's check that. Deliver 10 products to shop number A. We have one product remaining for type 1. Deliver that one product to shop B. Okay, product 1 is finished. Jump to product number 2. Deliver and all of the products to shop number C. No products left. Deliver no product to the rest of the stores. In this case, the maximum is 10. So 10 is also achievable. Okay. So what is the highest amount I can achieve? The maximum of the quantity that I have, that is 11. I can't achieve 11 plus 1, that is 12. I can't achieve 12. I can achieve till 11. So you can also write here, this upper limit can also be replaced by this max of quantities array. Okay, while on the other side, can I achieve 2? Let's see how. Let's start delivering the products. Deliver 2 to the first store, deliver 2 to the second store, 2 to the third store, 2 to the fourth store, 2 to the next store, and we have delivered 10 products. We have left with only one product of type 1. Deliver one product to F. But second product is still remaining. We have all the 6 units remaining undelivered to any store. So how would I handle that? Not possible, because we can deliver a product of only one type to one store. So they are undelivered. That means it is not possible to achieve 2 in this case. Okay, so that's how we basically get an idea to get the final logic how to distribute products. Let's say the guest element is mid. Now I want to know if this is valid or not. How would I check that? I will simply iterate over the quantities of each product. Let's say the very first product has quantity 11. Then if I can't exceed mid, then to how many stores I can distribute this product to, such that the quantity delivered to each product must not exceed this mid. It would be 11 divided by mid, obviously, because let's say I just want to deliver mid units to each shop, and I can deliver these units to 11 divided by mid stores. Okay, in case 11 is not divided by this mid, then I will deliver the rest of the products, which are 11 modulo mid, obviously, to the next store. So to handle that, I would use ceil here. Why? Let's say mid is 3. I want to deliver at max 3 product to any shop. I cannot exceed this 3. So 11. So to how many stores I can deliver the product of type 1, which has quantity as 11? That would be 11 divided by 3. That is 3 shops. But we still have 2 more units of this product after delivering it to 3 stores in the quantity of 3 units. How many units we will have? 11 modulo 3. That would be 2 units. 2 units. Now the 2 units will be delivered to the 4th store. That means we can distribute this product, that is product number 1, such that it should not exceed this 3 to 4 stores. Okay, now I am counting the number of stores in this fashion. So I can distribute product number 1 to 4 stores. Okay, 4 stores. Now I jump to second product, which has quantity as 6. To how many shops I can deliver this product, such that the quantity delivered to each shop must not exceed this 3. It would be 6 divided by 3. Ceil of 6 divided by 3. And that is going to give me 2. I can deliver this to 2 shops. and that's all. These, we just had 2 products, so we would have 6 stores. I can deliver my products to 6 stores. Okay, now I want to minimize this. I want to deliver my products to minimum number of stores, because it is okay if some of the shops may end up receiving no product, but it is not okay that we have undelivered product to any shop. We must deliver all of the products to minimum number of shops. Now in this case, I can deliver my product to 6 shops such that quantity given to any shop does not exceed this 3. Now I have to check at the end if this 6 is less than or equal to the number of shops that we have. If it is the case, then that means yes, this 3 can be the potential answer. So we return true for this case. Otherwise, if this exceeds the given shops, then I will have to return false. Okay, so that's all we have to do in the boolean function. Just we are given an upper limit for the count of product which can be delivered to each shop. Just find the number of shops to which we can deliver these products such that the quantity delivered does not exceed the given amount, the upper limit, the guessed mid, and just count the number of stores and return if and check if the number of stores that we have counted are less than or equal to the given stores or not. If they are, then return true. If they are not, then return false. Okay, so I hope you got the idea. If you have understood the solution till now, go and implement the solution by yourself. After that, you can start watching the video right from here. The minimize maximum function, which takes in the quantities and the number of shops. This represents the quantities of the products of each type. Initialize a range, low to 1, high to very large number, 10 raised to the power 5. This can also be replaced by the maximum element present in this quantities array. Run the usual binary search. Find the middle element. Initialize a variable sum. So this represents the number of stores. The number of stores to which we can deliver the products given in this quantities array, such that the quantity delivered does not exceed this mid. Now I iterate over this quantities array. I count the number of stores I can deliver each product IT. Okay, so this is equivalent to saying ceil of the quantity of the current product, that is IT, divided by mid. This is equivalent to saying this thing. Okay, I'm just counting the number of stores to which I can deliver this current product, such that the quantity delivered must not exceed this mid. And in this way, I will count the number of stores to which I will deliver all of my products. And finally, I have to check if the number of stores which I have counted to which I delivered the products, such that the quantity does not exceed this mid. If they are greater than n, that means our mid lies on the bad side. It cannot be the answer. So in that case, reinitialize the range to mid plus 1 to high. That means I have to deliver a larger quantity of the product. Otherwise, reinitialize the range to low to mid or mid minus 1. While this mid can be the potential answer. Mid can be the potential answer because I could deliver the product to all of my n stores such that the quantity or the maximum product delivered does not exceed this mid. So this can be the answer. Fine. So at the end I will return this low, which will store the final answer to this problem. So this is just equivalent to implementing the first true in the very first video of this series. So I'm just implementing the first true. That's what I have to find, the first true here, this x. Okay, so I hope you got the idea. Let's discuss the time and space complexity. We can see that we are just performing a binary search and the range is constant. For any test case, we just have to perform the binary search over this search space of size 10 raised to the power 5, so that would give me log of 10 raised to the power 5, while for these number of iterations, log of 10 raised to the power 5, we have to iterate over the array here, that is n. So n multiplied by log of this is basically the time complexity, which is equivalent to something like 15n. Okay, so that's the time complexity, n log m equivalent to n 14n, let's call it 14n, while the space complexity is constant because I'm not using any extra space to store anything. Fine, so let's jump to the code implementation part. Okay, so this is a solution class. We have a minimized maximum function which takes in this quantities array, the number of shops that we have, initialize the range low to 1, high to 10 raised to the power of 5, and run the usual binary search, find the middle element, okay, and initialize a variable sum to 0, iterate over this quantities array, count the number of stores, check if the number of stores exceeds n. If it is the case, then the search space will be reduced to right half. Low will be reinitialized to mid plus 1 because this is a bad mid. We don't have answer in this range. The new range would be mid plus 1 to high. Otherwise, this can be the potential answer. So the range for the very first true would be from low to mid minus 1, while at the end I will return this low, which is going to store my answer. So this is the implementation of this solution in C++. Let's see the implementation in other languages. So let's implement the same solution in Python, in Java language. So public int minimized maximum, which takes in an array list. Array list is basically equivalent to vectors in the C++. So array list of integer, call it quantities, and the number of shops. Initialize two pointers, low to 1 and high to 10 raised to the power of 5. Run the usual binary search, find the middle element, initialize a sum to 0, iterate over this quantities array, and count the number of stores to which I can deliver this product. That would be quantities I plus mid plus 1 divided by mid, which is just equivalent to saying ceil of it divided by mid, and check if this sum exceeds the number of shops. If it exceeds, then reduce the search space to right half. Otherwise, reduce the search space to the left half, while this mid can be the answer, and at the end return this low. Okay, so this is the implementation in Java language. Okay, so let's see the implementation in Python. So this is the implementation of the same solution in Python. So that's all for this video. If you like the video, then hit the like button and stay tuned with me in this series. We are about to end this series after a couple of problems, so I hope to see you all in my next video.